In 1926, quantum mechanics was at a crossroads. There were two different theories that led to the same results, but had wildly different frameworks. One was based on matrices, and the other on waves. Then came a genius that unified these two approaches. He showed that they were really just alternative formulations of the same thing, leaving us with quantum mechanics as we know it today. John von Neumann might be the most intelligent person to ever live. Game theory, set theory, the modern computer, and even the atomic bomb are just a few of the areas he pioneered as a mathematician. When he was only 6 years old, he could divide 8-digit numbers in his head. By 8, he had already mastered calculus. And throughout his life, he had the ability to read a book about almost any topic just once and have it entirely memorized. As one of his colleagues would describe him, von Neumann seemed to belong to an entirely different species. But before this genius could discover the right mathematical foundation for quantum mechanics, the work of two physicists was needed to set the stage: Paul Dirac and Pascual Jordan. The first step in unifying Heisenberg's matrix mechanics and Schrödinger's wave mechanics came in 1927 when Dirac and Jordan both found essentially the same formalism completely independently of one another. This formalism tied together both versions of quantum mechanics into one theory, which came to be called the Dirac-Jordan transformation theory. Unfortunately, this unification came at a cost: lack of mathematical coherence. As von Neumann described it, improper functions with absurd properties played a decisive role in the theory. So where did this absurdity come from? And how did von Neumann fix it? In order to answer these questions, we turn to a paper published that same year by von Neumann. In it, he describes why the Dirac-Jordan attempt at unification fails and the ingenious way he fixed it. The best way to understand von Neumann's paper is by first focusing on a fundamental aspect that both matrix mechanics and wave mechanics have in common. Atomic systems are connected to eigenvalue problems. An eigenvalue problem is a mathematical problem in a beautiful subject called linear algebra. Essentially, it boils down to solving this short equation, which says that if you have a vector v and apply some transformation t to it, it gives the same result as multiplying the vector v by some number. The vector v is called the eigenvector, and the number lambda the eigenvalue. Intuitively, this means that applying the transformation t to v is the same thing as just scaling v by the number lambda. Solving this equation then boils down to finding the eigenvectors and corresponding eigenvalues which make this expression true. But linear algebra is incredibly powerful. The eigenvalue problem doesn't just apply to 2D arrow vectors. It also applies to more exotic situations, where you can have abstract vectors like functions living in their own abstract vector space. And lambda can in general be a complex number. Now, the eigenvalue problem appears in both matrix and wave mechanics, but it is precisely in the type of eigenvalue problem that they differ. In matrix mechanics, for a given atomic system, the problem is to find the eigenvector v that satisfies this expression, where H is a matrix and E is an eigenvalue corresponding to the energy. The possible vectors that we could find here turn out to be infinite dimensional, and they must satisfy the following requirement, meaning that if you square all their components and sum, the result converges to a finite number. In wave mechanics, on the other hand, the eigenvalue problem changes. E remains an energy eigenvalue, but H is no longer a matrix. Instead, it is now a more general linear operator that acts on a function which satisfies the following condition. Now, according to von Neumann, here is the essence of how Dirac and Jordan attempted to unify these two approaches. First, consider the matrix mechanics eigenvectors. They are sequences that are indexed by discrete values 1, 2, 3, and so on. Call the space of these discrete values Z. Next, consider all the wave mechanics eigenvectors, which are these functions. They will be defined over some domain, typically of 1, 2, or 3 continuous variables that can be finite or infinite. We'll call this domain omega. We then assume that there's some more general space called R, and that Z and omega are just two particular instances of R. So R can be either discrete or continuous. With all this in mind, the eigenvalue problem in matrix mechanics can be written as a sum over all the discrete values, where this expression is valid for every component of the eigenvector. In other words, we have a summation over Z. And the corresponding wave mechanics problem for a function of x can be written as an integral over omega, where the function h here is called the integral kernel. Considering this in the context of the larger space R, we can now view both of these equations as just specific instances of integration over R, with one case being discrete and the other continuous. Von Neumann was not happy with this unification and described this analogy as superficial if one considers mathematical rigor. The reason is the following. First, consider the case where omega is the real line. And recall that the left-hand side here is a way of rewriting this expression. So whatever linear operator h we have below, it must somehow be represented by an integral kernel function above. Now consider the simplest possible linear operator, the identity operator. Meaning if you apply the operator to f, f just gets mapped to itself. The integral kernel corresponding to it then needs to be the following, which is called the Dirac delta function. If you haven't seen this before, it's a function that is zero everywhere except where x equals y. And at this point, it is essentially an infinite spike so that the integral over a region containing it equals 1. The Dirac delta nowadays shows up all over the place in physics, but at the time, it was controversial. Dirac invented it and described it as merely a convenient notation. Von Neumann thought it was a mathematical fiction, and for this reason believed there was something very wrong with the Dirac-Jordan approach. According to him, the spaces Z and omega are in reality very different, and every attempt to relate the two must run into great difficulties. Von Neumann's great insight, however, was to realize that though these two spaces are indeed different, something incredibly interesting occurs if you instead focus on the functions that can be defined on these spaces. Rather than trying to relate Z and omega, we should instead try to relate the functions over Z with the functions over omega. A fair warning here, I will try to be as intuitive as possible, but things are going to get a bit abstract now. However, I encourage you to stick with me. The payoff will be very satisfying, and you will be able to see how von Neumann established a beautiful link between quantum mechanics and a mathematical theory called functional analysis. We begin with omega. Intuitively, you can think of it as the real line, but abstractly, it's really some general continuous surface. Von Neumann writes that it can be any dimensional with or without boundary, finite or infinite. If you now imagine some function over the real line and try to integrate it, it would look like this. Similarly, an integral of a function over some general omega would be written like this. Now we consider all the functions defined on omega for which the squared integral is finite. These functions can in general be complex, so the square will be written like this. For brevity, von Neumann says we can also write it as follows. Interestingly, about 10 years later, Dirac would invent his own notation that would turn von Neumann's expression into this, which should look very familiar to you if you've ever taken a quantum mechanics class. Von Neumann continues and then says that we can call two functions f and g perpendicular or orthogonal if q of fg equals 0. In effect, what he's done has been to take the intuitive geometric properties of the 2D plane and carry them over into the abstract realm of a space of functions. So just as we can recognize two vectors as perpendicular, we can do the same with functions. With this definition, von Neumann can now speak about the length of functions in addition to the angles between them. The technical description is that he has defined an inner product over this space of functions, and it has become something called an inner product space. This particular space is called L2. If we now go back to the space Z, we can consider all the sequences for which the squared sum is finite. Now, sequences are really just functions as well. They map the numbers 1, 2, 3, and so on to certain values. And if we have two different sequences, we can define a similar sense of orthogonality like we did with the space of square integrable functions. Except this time, we say that two sequences x and y are orthogonal if when you multiply their components in this manner and then sum over them, you get 0. This creates a whole new inner product space. The space of all square summable sequences, or as it's better known, little L2. Now, here's the thing. Von Neumann was a pure mathematician. He did his PhD in set theory, and soon after began working with the great mathematician David Hilbert. Hilbert was also a pure mathematician, but at the same time had a keen interest in physics. And it was while working under Hilbert's mentorship that von Neumann began to develop his own interest in quantum theory. So with this background, von Neumann was uniquely qualified to apply the crucial key that would unify matrix and wave mechanics. He knew about two very important math theorems, the Parseval theorem and the Riesz-Fischer theorem. If you want a technical description of these theorems, just pause the video here. But essentially, the Parseval theorem says that you can map sequences in little L2 to functions in L2. And the Riesz-Fischer theorem says that you can map functions in L2 to sequences in little L2. Taken together, this means that L2 and little L2 are mathematically the same. They are isomorphic. In other words, the various sequence and function spaces which underlie quantum mechanics are in essence and with absolute mathematical rigor identical. So anything that can be done in matrix mechanics can be done in wave mechanics, and vice versa. The two versions of quantum mechanics have been unequivocally united in a deep mathematical sense. But von Neumann wasn't finished yet. He went on to spell out an entire mathematical theory of what these two spaces actually were. These two spaces are really just two instantiations of something he named a Hilbert space. L2 is then a concrete, continuous realization, while little L2 is a discrete realization. Intuitively, a Hilbert space is just a vector space that has an inner product defined on it and is complete. Which means that anytime you have a sequence of points that become arbitrarily close to each other, their limit exists in the space. I made an entire video going into detail about Hilbert spaces, so if you're interested in going deeper, check it out after this video. Over the next few years, von Neumann wrote two more papers, further developing his new unified version of quantum mechanics. His theory was completely mathematically rigorous and made no use of the absurd mathematical fictions von Neumann disliked so much in the Dirac-Jordan transformation theory. Interestingly, about 20 years later, Lorentz Schwarz developed the theory of distributions and finally found a proper mathematical understanding of the Dirac delta as a distribution rather than a function. The concept of a Hilbert space proved to be pivotal in allowing von Neumann to discover the right framework for capturing the essentials of quantum mechanics. His three papers were further refined and then summarized in an excellent book in 1932, giving us quantum mechanics as we know it today. A beautiful theory that flows from 5 foundational axioms and is the most accurate scientific theory ever created. But there's a lot more to science than just quantum mechanics. If you're interested in learning about circuits, scientific thinking, computer science, or even refreshing on fundamental math, I highly recommend this video's sponsor, Brilliant.org. Brilliant is jam-packed with interactive lessons and personalized practice problems covering a truly comprehensive curriculum designed for people of all ages. The best part is, Brilliant encourages an active approach to learning, so you'll always be learning by doing. Lately, I've enjoyed going through their new Python course. It's been a great refresher for me and has encouraged me to write more efficient code. So if you'd like to give it a try, Brilliant can help you excel in math, science, and coding. To start learning for free for a full 30 days, go to brilliant.org/abide by reason. Scan the QR code on screen or click on the link in the description. Brilliant's also given my viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant.